Swayam Prabha. Digital India. Educated India.
Welcome everybody. So, now in this class we will continue the generation of the carbene, this topic. In the last class we have discussed about the generation of the carbene from the diazomethane by the decomposition through the heat or under photochemical condition. After that we have learned that how the carbenes can be synthesized from the diazocarbonyl compounds and obviously the synthesis of the diazocarbonyl compounds also. Now, we will learn in another method of carbene preparation, that is carbenes from tosyl hydrazones. So, here the carbenes will generate as an reactive intermediate of the reaction, not as a starting material. What does it mean? That we have this keto compound and if we will use this reagent in presence of base, that tosyl derivative of this hydrogen, then that will give the corresponding tosyl hydrazone moiety. I am writing in place of tosyl this para-toluene sulfonyl. Okay. So, now we have this base which will pick up this proton. Okay. Once this will pick up, this will give the corresponding derivative, anionic derivative. Okay. So, now we have these lone pairs here. Okay. So, here this will come and this will eliminate. So, what we will get over here under heating condition? This will eliminate this para-toluene sulfonate group and will give here the corresponding diazo compound, that is okay. Here I would like to mention one thing, that in general when we have learned the living group things, what we have used to do, that let us say we have ROH, we used tosyl chloride and some base. Okay. So, what we prepare? RO tosyl or para-toluene sulfonyl group. Okay. So, now this is considered as a very good living group. Okay. Because if you put some nucleophile, it will attack over here and this will go. Okay. But in this case you see there is a very unusual or uncommon leaving group that is eliminating to generate this diazo compound. Okay. So, that is nothing but this is called para toluene sulfonate. Okay. But what we previously knew that para toluene sulfonate, that is the better leaving group, but here what is the leaving group? Here it is leaving group is para toluene sulfonate group. Okay. So, that gives our desired diazo compound. Okay. So, it is important to remember here this is not the para toluene sulfonate group, rather this is para toluene sulfonate group. Okay. Now, under heating conditions what will happen? Now, under heating condition or more strongly heating condition, more strong heating condition. So, the nitrogen will eliminate, and definitely this is in aprotic solvent I am talking about, because in protic solvent the reactions will work in different way that will generate some carbenium ion, but in this case this will give the corresponding carbene in aprotic solvent. Okay. This is important, aprotic solvent. Okay. So, this will generate the corresponding carbene, and now this carbene will react in this way. Okay, to give the corresponding olefin. Okay, this is the mixture of olefin it will form, and this is called, this is a name reaction, this is called Bamford-Stevens reaction. What it is called? Bamford-Stevens reaction. Okay. So, here this will give such kind of olefin which is a mixture of E and Z, and that will give this Bamford-Stevens reactions. We will learn many reactions or applications of these Bamford-Stevens reactions, and we will see many new reaction or new applications in later stage of this course. Okay. Next we will see the carbene formation from or via alpha elimination. So, another technique of carbene generation, that is called carbene formation by alpha elimination. Okay. So, before that we have to learn what is alpha elimination. Do you know what is beta elimination? We have learned this, okay, when we have studied in the first year that elimination reactions, we have learned about this beta elimination. I am just showing inside some kind of, as per example like this. So, you have hydrogen, let us say you have R prime, something like this, or then you have base, it is picking up this and this hydrogen, and it will give you the corresponding olefin. Okay. So, now this is the, let us say alpha, this is the beta. Okay. So, this is called beta elimination, this is the beta elimination. So, here we need to know the alpha elimination, right. So, what is alpha elimination? Elimination in which the proton and the leaving group both are located in a same atom. Okay. That is called alpha elimination. Okay. So, elimination in which both the proton and leaving group located at the same atom. Here we will see that both these proton and the leaving group are actually located at the same carbon atom. As per example, if we take chloroform, okay, and due to this inductive effect of these 3 chlorine atom minus I effect rather, this is pretty acidic. So, this proton is pretty acidic. So, this is acidic proton. Okay. So, now base can easily pick up this proton, okay, to generate the corresponding anion. Okay. So, now from here chlorine can liberate as a leaving group, and once it will liberate from this anion, this will generate the corresponding dichlorocarbene. So, this is the dichlorocarbene. This is one of the very common reaction to generate such kind of dichlorocarbene. Okay. Similarly, we can use its dichloro derivative as per example like this, but here obviously you need more strong base, because there you have 3 chlorine atom attached to this carbon atom or carbon center, but here there are only 2 chlorine atom. So, you need more strong base. As per example, we have used here LDA. Okay. What is LDA? Lithium diisopropyl amine, that is one base. So, this is a very strong base. Once you will use that, so that will pick up this proton and generate this corresponding anion. Okay. And once it will generate, this will give the corresponding carbene. Okay. Similarly, if we use the monochloro derivative, okay, that also can generate the carbenes. How? Only thing is that here, irrespective of previous way, there are less number of chlorine atom. So, these hydrogens are not that much acidic like previous way. Only thing is that here we have to use more stronger base. Okay. So, as per example, here we have used this base, okay, and this will generate the corresponding anion, and after liberation of chloride, so this will give the corresponding carbene. Okay. So, in this way, starting from these chloro derivatives, we can synthesize the corresponding carbenes. Okay. In another way, if we use diiodomethane in presence of zinc copper couple, this can give this zinc compound, and then this will give this zinc carbenoid basically, and it can stay like this way also. Okay. So, these are called zinc carbenoid. We have learned that what is carbene and what is carbenoid. So, in this case the metal is the zinc one. So, here that will give these corresponding zinc carbenoids, and this has been used enormously in a very well known and famous reaction that is called Siemens-Smith reaction. Siemens-Smith reaction. Obviously, we will learn many applications of this particular reaction in our later stage, when we will learn the reactions and rearrangement of carbenes. That time we will specifically go through these particular reactions also, that is called Siemens-Smith reactions. Okay. Now, so far whatever this carbene generation we have shown, that most of the cases what we found, that we need the base to generate the carbanion, and then that will by leaving something or some group that gives the corresponding carbene. Now, if the compound that is going to react with this carbene, if that is base sensitive, what will happen? So, we are generating in situ, because carbenes anyway you cannot store, or you cannot basically use it for other purpose. Rather, what we have to do, we have to generate it immediately, and then we have to use it. Okay. So, for that what we have to use, that when your starting material or some of your substrates of choice you want to react with carbene, if that substrates of choice is base sensitive, then what will happen? In that case, definitely we cannot use those techniques. Rather, if the substrate of choice, we can write substrate of choice is base sensitive, what will happen? Okay. So, in that case the carbene has to be generated in absence of base, okay. Otherwise that base can destroy our substrate. So, overall the reactions will not occur. Okay. So, in that case what we will do, let us say here the carbene can be generated from this carboxylate also, by decomposition of this carboxylate, just by heating, this will liberate the carbon dioxide, and this sodium trichloroacetate, this compound called sodium trichloroacetate, that will liberate the corresponding carbon dioxide, and once that will liberate the carbon dioxide, what that will generate? That will generate this trichloro based carbanion, and once this trichloro based carbanion generated, so that actually can easily give this dichlorocarbene which we need. See, here we have not used any base to synthesize this carbene. Okay. So, in this case we can avoid the use of base, so that our desired reaction should happen. Okay. In another way, we can use the organomercury compounds for the preparation of the carbenes. Okay. So, these can be also used to generate carbene. How? That let us say, as per example, we can take this type of substrate, if we see this carbon mercury bond, that is more covalent than the carbon lithium or other carbon metal bond. In this case, what we will do, that we will simply go for thermal decomposition, and once you will do the thermal decompositions, this will simply generate this dichlorocarbene, okay, with this molecule PHGBr, fine. Similarly, in another case, we use this particular compound in presence of chlorine, this CF3 group, okay, that also under heating condition will generate this carbene with similar phenyl HGBr. Okay. So, from organomercury compounds also we can easily synthesize these kind of carbenes in absence of base. So, these are the ways that we can synthesize the carbenes without base presence. Okay. Next is that in another way we can synthesize very stable carbenes. Okay. We have learned about this persistent carbenes. There we came to know that these type of carbenes even sometimes stable and isolable. So, we will learn how this type of carbenes can be synthesized. Okay. So, carbenes formation by deprotonation. So, these type of carbenes can be synthesized from these, from its corresponding n heterocycles via the deprotonations. As per example, we can see that we have this imidazole moiety and okay. So, in presence of alkyl halide, this will again give corresponding dialkylated product. Okay. Now, this is acidic proton. If you use the base, that will pick up this proton, and once that will pick up, then what will happen? Then that will actually generate the corresponding anion. Okay. And you will have this, you will have this. Okay. Now, these can stays like a carbene. Okay. So, these are the corresponding carbenes. Now, these can be also in resonance. Okay. So, another resonance structure. Okay. So, these are the carbenes that we can generate through the deprotonations. Okay. These are called n heterocyclic carbenes, and we have seen its enormous use in recent days in various type of transformations, okay, because of its stability, because of its versatility. If you see these R groups, you can actually play around these R groups, and even we can go for this various asymmetric reactions using these n heterocyclic carbenes. Okay. Lot of enantioselective reactions also you can use. If you use here all these chiral, here this chiral part, then you can actually go for various asymmetric synthesis. Okay. Now, the next is that the synthesis of these carbenes from small rings. So, carbenes from small rings. So, if some rings that are small, that are in general strained rings, especially if you take all the 3 member rings, they are very strained. So, under heating or photochemical conditions, that generates the carbene at the corresponding stable fragment. So, this is important that after the decomposition, that small rings has to give some stable fragment, so that it can generate the corresponding carbenes. As per example, if you take this cyclopropane moiety under photochemical decomposition, this will give the corresponding carbene plus the stable fragment, that is this ethylene. Similarly, if you take this substrate, this dihydrophenanthrene type of substrate with the corresponding cyclopropane ring under photochemical decomposition, again this will give the corresponding carbene, okay, with the phenanthrene moiety. Okay. Similarly, if we take the corresponding epoxide under similar type of photochemical decomposition, it will give the corresponding carbene with benzaldehyde as a stable fragment, and for norbornadiol ketal derivative also gives under thermal decomposition, give this stable benzene plus dimethoxy carbene. Okay. Similarly, like ketene type of moiety also under photochemical or thermal decomposition will give the carbene plus carbon monoxide elimination gives this carbene. Here this is also stable fragment, okay, stable molecule, and similarly decomposition of diazirine rings, that also gives under thermal decomposition give this carbene moiety with the nitrogen elimination. Okay. So, with this, thank you all for today's lecture.